In Hive, data typically resides as flat files in HDFS. A Hive table is a logical concept that is made up of a number of files in HDFS. In simpler terms, tables are just files stored in subdirectories in HDFS. There are two kinds of tables in Hive: internal managed tables and external tables. As the name suggests, internal managed tables exist in HDFS, and Hive controls the entire life cycle of their data. Hive stores the data for these tables in a subdirectory inside a warehouse directory. With internal tables, the data and table are tightly coupled. When an internal table is deleted, both table and the data, including the metadata, are deleted by Hive. External tables reference remote data that is stored outside of Hive. With external tables, there is no need to move data into the Hive warehouse directory. The schema and metadata are loosely coupled with the actual data. With external tables, when a table is deleted, only the metadata gets deleted. The actual data is left untouched. This is like deleting a shortcut icon for an application on your computer's desktop. External tables come in handy when data is going to be used by multiple databases or when you need multiple schemas for the same underlying data. A good example would be analyzing data from stock markets. The same data set will be used by different tools and might be analyzed concurrently under different schemas. Views in Hive are similar to views in traditional relational databases. They allow a query to be saved and treated like a table. Views are a logical construct and do not store data like a table. Views reduce query complexity. Hive evaluates the view and then uses the results to evaluate the query. This view retrieves data containing details about graduate courses in the state of New York. Within a Hive table, a partition defines how to physically split the data on the disk. Hive efficiently performs queries on large data sets and is very good at queries that require full table scans. For queries where you want to limit the data to be retrieved or processed, for example queries having where clauses or other filtering clauses, it is important to organize the data properly and to tell Hive about it. Partitions accomplish this task. Click the button to learn more. We can identify columns with relatively low cardinality, like geographies or dates, and high relevance to key queries, and create virtual columns or partition columns to identify data that satisfy a certain criteria. Think about the concept of searching for the word adequate in a dictionary. You would search for that word in the A section on the page, having the index add, and you would exclude all the other pages in the dictionary from your search. When we partition data based on things like date, location, or any other relevant keys while querying, we will act only on data relevant to that partition, excluding the majority of non-relevant data. Without partitioning, Hive scans all data in the directory and applies the query filters on the entire data set, which can be a very slow and costly operation. In this example, common reports and queries might be generated based on the location of universities. For example, we might want to query details about graduate courses available in the state New York from a centralized table holding data about all graduate courses available in the U.S. If we define location state as a column partition during table creation, then data gets categorized using this partition. This will allow Hive to skip all but the relevant subdirectories and data files while querying based on location. In our case, only the partition for the state New York will be accessed when we run the query. This can lead to tremendous reduction in data to be read and filtered in the initial map stages. This also reduces the number of mappers, I/O operations, and ultimately the time required to run the query. Bucketing is another technique that allows you to organize your data from tables and partitions by decomposing it further into multiple parts or buckets. Once you define partitions, data in each partition may in turn be subdivided into buckets, providing further granularity and organization of the data. This is accomplished by reading each record and placing it into one of the buckets based on some logic or algorithm. We can use bucketing to avoid too much data slicing. We can avoid situations that might require creating thousands of tiny partitions by using bucketing. In Hive, a partition is a directory, but a bucket is a file. Buckets are more efficient for certain types of queries, such as join operations. Sampling queries are more efficient when performed on bucketed columns. Bucketing results in more evenly distributed data. In the world of SQL Server, indexes are critical for improving efficiency and performance. They are effective in retrieving rows from tables. If there is no index, a full scan of all the data is needed to retrieve the required rows. This is time-consuming and inefficient. With Hive, we are typically dealing with big data, and doing a full scan on huge volumes of data will degrade performance drastically. So indexing is especially critical in Hive. Indexes in Hive function is more like non-clustered indexes in SQL Server. Rather than containing the actual row data, Hive indexes contain the indexed column values and a pointer or offset to the location of the data. Currently, compaction and bitmap index types are available in Hive. More index types will be available in the future. The Hive Metastore is a centralized repository for Hive metadata. It stores the information about the tables, partitions, schemas, columns, types, and table locations in HDFS. The Metastore is the bond between Hive and HDFS. It tells Hive where your data files live in HDFS. The Metastore is comprised of a Metastore service and the backing store for the data. Using a Thrift interface, this information can be queried or modified. As a result, it provides clients, including Hive, access to this information via the Metastore Service API. Any client that needs to access a Hive table can access it through Metastore. By default, the Metastore uses an embedded Derby database on the local file system to store the information. The Derby database is included in the Hive distribution. We can also create a Metastore using any RDBMS and can give different user access to Hive table details through the RDBMS. In the diagram, we can see three kinds of metadata storage. Data stored in the Derby database can support only one active user at a time and is not certified for production use. In local mode, the Hive Metastore service runs in the Java Virtual Machine Hive server process, but the Metastore database resides in a separate RDBMS. This is useful when you want external applications to do pre-processing and querying on the metadata information. In remote mode, one or more Metastore servers runs separately from the Hive service. This provides better manageability and security, since the database tier can be completely firewalled off and the clients no longer need the database credentials. Hive supports numerous file formats for storage, including RC file and sequence file. RC file, or record columnar file, is a data placement structure that determines how to store relational tables on computer clusters. It is designed for systems using the MapReduce framework. It provides fast data loading, fast query processing, highly efficient storage space utilization, and adaptivity to dynamic data access patterns. ORC file, or Optimized Row Columnar file format, provides a highly efficient way to store Hive data. It was designed to overcome limitations of the other Hive file formats. Using ORC file improves performance when Hive is reading, writing, and processing data. Sequence file is a flat file consisting of binary key-value pairs. It is extensively used in MapReduce as input-output formats. Also, the temporary outputs of maps are stored using sequence file. Sequence file provides writer, reader, and sorter classes of writing, reading, and sorting respectively. There are three different sequence file formats. Uncompressed key-value records. Record compressed key-value records where only values are compressed, and block compressed key-value records where both keys and values are collected in blocks separately and compressed. The size of the block is configurable. Hive includes data types that are similar to the data types available in other SQL dialects. Hive data types fall into two categories: primitive and complex types. Click each button to learn more. Primitive data types include numeric types, date-time types, string types, and miscellaneous types, such as Boolean and binary. Complex data types include arrays, maps, structs, and unions. Numeric types include almost all of the similar data types used in other SQL dialects. Click on each of the buttons to learn more about the numeric data types. Date is similar to the SQL date data type, and the values are represented according to the Gregorian calendar. Time values are represented according to the 24-hour clock. The timestamp data type supports traditional Unix timestamp with optional nanosecond precision. Timestamps are interpreted to be time zoneless, but time zone is available using the conversion UDFs provided by Hive. Click the clock to learn more. String literals in Hive are expressed with either single quotes or double quotes. Hive uses C-style escaping within the strings. Varchar types are created with a length specifier, which is the maximum character limit allowed. If a string value exceeding the length specifier is assigned to the varchar, the excess value is truncated. Char types are very similar to varchar types, but they are fixed length with a maximum length of 255 characters. If the values are shorter than the specified length, then the value is padded with spaces. Miscellaneous types include Boolean and binary. Boolean data types hold true or false values. Boolean columns in Hive tables that contain null are treated as false. Binary data types hold an array of bytes. When working with big data, a database row might be very wide with hundreds of columns. If you are only interested in a few of those columns and don't care about the other columns, you can simply declare those column types as binary, and Hive will try not to interpret them. Click each button to learn more. Arrays contain elements of the same type as an indexable list. Elements can be accessed using the n notation, where n is an index into the array. Maps contain elements in the form of key-value tuples. Structs contain elements of different data types. A dot notation is used to access the elements within the type. Union types can hold only one of their specified data types at any given point in time. Many data types may be declared, but only one type can be used. You can create a union type using the Create Union UDF. Sometimes, queries cannot be properly written using Hive's built-in functions. In those cases, UDFs or user-defined functions can be used. Creating UDFs for Hive is simple and very similar to creating a function in Java. Let's look at a use case. Let's create a UDF for timestamp conversion. Sometimes when working with weblogs, we might encounter Unix timestamp values that are not readable. We can write a custom UDF to convert a Unix timestamp into a more readable format. When this custom method is used in a Hive query that retrieves a timestamp, the timestamp is automatically converted into a readable format. In this example, a query might return an illegible timestamp in Unix timestamp format. When we use a custom UDF in the query, the output timestamp field will appear in a readable format. This sample shows the code you might use to create a custom UDF for converting Unix timestamps into a readable format. To implement this solution, follow these steps. Create a jar file that contains the UDF and add this jar in the Hive prompt. Create the Hive function using the command shown on the screen. You can test the solution by running the query with and without the custom UDF. Once we create a table in Hive, the next step is to feed data into the table for processing. Using Hive DML or Hive Data Manipulation Language, there are two primary commands you can use to load data into Hive tables: load and insert. Load operations are purely copy and move operations that move data files into locations corresponding to Hive tables in HDFS. Hive does not do any transformations while loading data into tables. Click the button to learn more. Take note of the following key points. No verification of data against the schema is performed by the load command. If the file is in HDFS, it is moved into the Hive-controlled file system namespace. Loading data from HDFS will result in moving the file and directory. As a result, the operation is quite fast. Query results can be inserted into Hive tables using the insert command. The insert command can be run on a table or a partition. If the table is partitioned, you must identify a specific partition of the table by specifying values for all of the partitioning columns. Hive can insert data into multiple tables. Using the insert command, multiple insert clauses, also known as a multi-table insert, can be specified in the same query to insert data into multiple tables. There are two types of inserts available. Click each button to learn more. Insert Overwrite will overwrite any existing data. Insert Into will append data to the table or partition, keeping the existing data intact. The select clause is similar to the projection operator in SQL and is used to retrieve data. A basic select query structure contains a select clause, which scans the table specified by the from clause, a where clause, which specifies what to filter, a group by clause, which specifies a list of columns and how to aggregate the records, A sort by clause, which specifies a sort order for the specified column. Order by, cluster by, and distribute by clauses, which specify the sort order and algorithm. And a limit clause, which specifies the number of records to retrieve. The order by clause in Hive is similar to the order by clause in other SQL dialects. It performs a total ordering of the query result set. When using the Hive order by clause, all data is passed through a single reducer. If the number of rows in the output is too large, the single reducer could take a very long time to finish running. To avoid this performance issue, the order by clause can be used in strict mode, where it is followed by a limit clause. The limit clause restricts the number of rows to be scanned for execution. The sort by clause performs a local or partial ordering of the query result set. Hive uses the columns specified in sort by to sort the rows before feeding the rows to a reducer. Sort by orders the data within each reducer, performing a local ordering, where each reducer's output will be sorted. Since data is ordered only within each reducer, it only guarantees ordering of the rows within a reducer. If there is more than one reducer, sort by may produce partially ordered final results. The sort order will be dependent on the column types. If the column is of numeric type, then the sort order is also in numeric order. If the column is of string type, then the sort order will be in lexicographical order. The join clause combines records from two or more database tables. Hive joins are simple and straightforward. Hive joins can be classified as inner joins or outer joins. An inner join creates a new result table by combining column values of two tables. The query compares each row from the two tables to find all pairs of rows that satisfy the join predicate. An outer join does not require each record in the two joined tables to have a matching record. The joined table retains each record even if no other matching record exists. A map join is a special type of join where the smaller table is loaded in memory and the join is performed in the map phase of the MapReduce job. Since no reducers are required, map joins are much faster than regular joins. Use map joins only if one of the tables in the join query is small enough to fit into memory. Click the button to learn more. A semi-join is a half join, meaning that the result contains only rows from one of the two row sources. Only equality joins, outer joins, and left semi-joins are supported in Hive. Hive does not support join conditions that are not equality conditions. More than two tables can be joined in Hive. Implicit join notation is supported in Hive version 0.13.0 and later. The union clause is used to combine the results from multiple select statements into a single result set. Note that Hive currently supports only the union all clause. This is commonly referred to as a bag union, and it does not eliminate duplicate records. When performing a union, the column count and column names returned in each of the select statements must be the same. Like subqueries, the result of the union can be passed into another query. A subquery is a query within a query and is used to return data that will be used in the main query. Hive supports two types of subqueries: subqueries using the from clause and subqueries using the where clause. Note that subqueries using the from clause require the as name clause since every table in a from clause must have a name. The union operation can be used in a subquery. Multiple levels of subqueries are allowed in Hive. Please note that references to the parent query are not supported when using a from clause subquery. For subqueries using the where clause, the result of the query can be treated as a constant. This constant value can be used for in and not in statements. These are called uncorrelated subqueries because the subquery does not reference any columns from the parent query. Similar to in and not in statement, exists and not exists clauses are also supported. References to the parent query are supported when using the where clause. Virtual columns are not part of physical Hive tables and are computed on the fly. They are a feature used primarily for error diagnosis. Click the button to see a scenario. Consider a scenario where you want to find a specific set of data as well as the input file it came from. For example, we might be searching for data related to Einstein in ebook data files and want to know the input file containing this term. We can use the virtual column query shown here. Hive provides the export and import commands to let users move data between Hive and RDBMSs. Click each button to learn more. The export command is used to export data out of Hive. You can export data from a table or partition along with the metadata into a specified output location. The exported data is stored in JSON format. Using the import command, data can be imported back into another database or Hive instance. Sampling lets you run queries on a smaller set of data instead of an entire table to reduce query running time. Sampling offers a trade-off between speed and accuracy. Common uses of sampling include predictive analysis and trend analysis. There are two types of sampling: sampling bucketized tables and block sampling. Click the buttons to learn more. Sampling bucketized tables lets you sample data from selected buckets in an HDFS table. Block sampling lets you specify the percentage of data to be sampled. AWS provides an end-to-end platform for big data solutions. AWS extends Hive functionality with new features and functionality that are key in developing world-class big data solutions. Amazon Elastic MapReduce can enhance the reliability and scalability of your Hive applications. AWS services can be used with Hive to deliver analytics, monitoring, and business intelligence solutions. Click the button to learn more. AWS provides an easily scalable environment for your Amazon EMR and Hive application with minimal downtime. Low cost and flexible resource availability to efficiently scale applications. With AWS, you pay only for the services and resources you use. Flexibility to run Hive CLI both from within and outside of Amazon EC2. This is very helpful with development and deployment activities. Enhanced security features like Amazon VPC or Virtual Private Cloud to isolate your Hive application running with Amazon EMR into an isolated network that you define. Managed storage options like DynamoDB, a scalable NoSQL database service that makes it simple and cost-effective to store and retrieve any amount of data. Efficient monitoring tools like CloudWatch to monitor cluster performance and raise alarms. This can be very useful when running critical Hive batch processes. Useful business intelligence tools like MicroStrategy with built-in Hive connectivity. Hadoop application support and seamless integration with other AWS services. And finally, Hive updates are managed as part of the managed services in AWS. Amazon EMR provides some key Hive-specific features. The ability to directly read from and write to Amazon S3 with Hive. The ability to load table partitions automatically from Amazon S3. The ability to specify an off-instance metadata store. This feature lets you override the location of the metadata store to use. The ability to access critical resources located in Amazon S3. This lets you reference resources such as scripts for custom map and reduce operations, or additional libraries located in Amazon S3 directly with a Hive script. Follow the link for more information. Hive script. HiveQL queries that need to be processed can be written in a script or HQL file and stored in an Amazon S3 bucket, which will be accessed by Amazon EMR for processing. Input. Input data can be loaded into Amazon S3 or HDFS. Amazon EMR nodes can read and write data directly to Amazon S3. Output. Amazon EMR supports creating output directly in Amazon S3 and HDFS. Logs. In Amazon EMR, log files are created in the master node. You also have the option of archiving logs in Amazon S3. Click the button to learn more. The standard log files are controller, which contains information about the processing of the step. If your step fails while loading, you can find the stack trace in this log. Syslog describes the execution of the Hadoop jobs in the step. Stander, which is the standard error channel of Hadoop while it processes the step. Standout, which is the standard output channel of Hadoop while it processes the step. Agency X, an analytics company, is engaged in a project for a leading online supply chain retailer. The project involves product analysis, such as determining the impact of new features of products in their inventory. Ad hoc analysis is performed based on user engagement and by measuring the click-through rate on that particular new feature. A deeper analysis may also be required to determine the impact based on geographical region. For example, the click-through rate for North America may be compared with the click-through rate for Asia. Click each button to learn more. The scenario requires the analysis of log datasets that are approximately 10 terabytes in size. These datasets hold more than 3 years of vital information in semi-structured format. Traditional business intelligence tools work fine up to a certain point, typically for data that is less than a terabyte. However, when the scale increases to many terabytes and petabytes, traditional solutions become inefficient. Also, BI tools work best with predefined structured data. In this scenario, the logs don't conform to a specific structure or schema. Knowing the limitations of traditional systems, Agency X, an analytics company, is engaged in a project for a leading online supply chain retailer. The project involves product analysis, such as determining the impact of new features of products in their inventory. Ad hoc analysis is performed based on user engagement and by measuring the click-through rate on that particular new feature. A deeper analysis may also be required to determine the impact based on geographical region. For example, the click-through rate for North America may be compared with the click-through rate for Asia. Click each button to learn more. Traditional business intelligence tools work fine up to a certain point, typically for data that is less than a terabyte. However, when the scale increases to many terabytes and petabytes, traditional solutions become inefficient. Also, BI tools work best with predefined structured data. In this scenario, the logs don't conform to a specific structure or schema. BI systems take time to execute, and querying such a large dataset will take a long time. Ad hoc analysis requires quick processing time. Knowing the limitations of traditional systems, Agency X opted to invest in new big data technologies that use Hive. The application is designed in such a way that it uses Flume to collect data and send it to HDFS storage. Hive performs the role of the analyzer. Scripts and ad hoc queries are run on top of this dataset to produce reports. Much of this type of analysis can be performed by using Hadoop, Hive, and regular SQL. Click the icon to learn more. The measurement of the click-through rate can be easily expressed as a join of the impressions and clicks for a particular link related to the feature. Hive is useful for assembling this kind of data and then feeding it into a data analysis engine. This information can be joined with geographic information to compute the effect of product changes on different regions. One can also compute the average click-through rate for different geographic regions by performing aggregations. All of these can be easily expressed in Hive by using SQL queries. Agency X was able to build their system by using a minimal cluster configuration and capacity. They can run their regular activities in a cluster of 50 virtual instances with the following configurations: 64-bit OS, 6 CPU cores, 1 terabyte of storage, and 12 gigabytes of RAM. By analyzing the data using Hive, the company gained tremendous insight into year-over-year sales patterns. Through the analysis, an unexpected seasonal purchase pattern was discovered, which helped the retailer to increase sales. The company realized reduced infrastructure costs compared to their previous solution environment. Agency X was able to reuse this model to implement similar solutions for other clients. Follow these links for more information.